A winged spaceplane dangles by cables 4.5 kilometers in the air beneath a military Chinook helicopter. It's a strange sight for a space mission. ISRO, India's space agency, is using this Chinook to execute a high-altitude release for its Pushpak demonstrator vehicle. This is an early-stage testbed, quite different from the X-37B, a fully operational spaceplane that already conducts long-duration, classified missions in orbit. To follow the engineering logic of the modern space race, hit subscribe. We have to look at why ISRO is dropping a spaceship out of a helicopter instead of launching it on a rocket. This test protocol targets the single largest financial burden in the industry. Throwing away multi-million-dollar rockets after one use is expensive, and mastering the return flight is the primary path to lowering that cost. Reusable launch vehicles, or RLVs, provide the only viable route to cheap space access. However, bringing high-value hardware back to Earth intact requires solving massive engineering bottlenecks. ISRO is reverse engineering the standard mission profile. They are starting their flight testing at the very end of the journey. This chart highlights the isolated variables. ISRO chose to master scorching re-entry temperatures and high-speed unpowered landings as separate engineering tasks before ever integrating the spaceplane with a rocket. Keeping the vehicle off a rocket during this phase reduces financial risk. It allows engineers to solve the exact physics problems that destroy reusable concepts during atmospheric return. In 2016, the hypersonic flight experiment began the sequence. ISRO strapped a version of this vehicle to a solid rocket booster and blasted it to Mach 5. Thermal survival was the only goal for this mission. The vehicle skipped the runway landing entirely, executing a simple splashdown in the Bay of Bengal. Surviving the heat required a specialized thermal protection system. ISRO developed high-purity silica tiles and carbon-carbon composites for the nose and leading edges to withstand the severe heat flux caused by atmospheric friction. After the vehicle survived the plasma of Mach 5 and hit the sea intact, the thermal barrier was cleared. ISRO moved to the next problem, the landing. Shifting focus from heat to precision, the landing experiments, or LEX, took place between 2023 and 2024. This diagram shows a central constraint. Spaceplanes have a low lift-to-drag ratio. They do not glide like commercial jets. Without an efficient glide, the descent is steep, forcing the vehicle to touch down at high speeds, between 320 and 350 kilometers per hour. This requires total autonomy. Without a pilot, the vehicle relies on radar altimeters and NAVIC receivers, India's regional satellite navigation, to calculate the exact moment to deploy parachutes and wheel brakes. Managing this much kinetic energy requires a perfect aerodynamic solution. It is a guided descent that must hit the runway threshold at a precise velocity to avoid a structural failure. LEX 01 established the baseline with a successful centerline drop and parachute stop. Following the flight, engineers used the gathered load data to reinforce the airframe structure. This top-down view shows the added difficulty for LEX 02. The helicopter released the vehicle from an off-nominal position, forcing the spaceplane to autonomously steer and correct its flight path to reach the runway. LEX 03 pushed the envelope further. The vehicle corrected for severe crosswinds and a massive 500-meter cross-range error, validating the advanced guidance algorithms. For LEX 02 and LEX 03, ISRO launched the exact same physical airframe and avionics used in the first flight. This demonstrated that the vehicle could be recovered and returned to flight without structural modifications. Reusing the same flight hardware through multiple high-stress drops moves the program from theoretical models to durable, operational reusability. ISRO has now de-risked the terminal phase. They have flight systems that navigate from off-nominal points, land in high winds, and fly again immediately. The next target is the Orbital Reentry Experiment, or OREX. Pushpak will be mounted to an ascent rocket, enter orbit, and fly back to a runway landing. Preparation is already underway at a new landing gear drop test facility commissioned in 2025. Engineers are using it to simulate the higher impact speeds and weights required for a return from orbit. This demonstrator is a step toward a reusable flyback upper stage, a technology designed to lower the cost of every kilogram sent to space. If you found this useful, hit the like button. By isolating and solving the landing problem through helicopter drops, India is building a reusable foundation for orbital flight before the first rocket ever leaves the pad.